Okay, thank you. Hello, everyone. Thank you for having me. So today I will speak about open and repurposable foundation models for the automotive industry. And I'll first start with the motivation for us. So why do we work on autonomous driving, right? So the thing is that, as you might know, but maybe you do not know the magnitude of this, is that there's lots of people dying on the road. So every year there's about 1.2 million people dying on the roads because of vehicle crashes. And in addition to that, you have about 50 million people that suffer injuries from vehicle crashes. So this is not just costly in human lives, which are tragedies, but also in money, as these accidents amount for, they're like that, amount for 3% of the GDP costs for most countries, right? And of course, most of, if not all crashes are due to human error, and there's ways to fix this with AI. So this has been a long-standing motivation in the automotive industry, how to improve the safety of the vehicles. And driving assistance is not a new topic and has evolved greatly across the years. So we originally had these modular-based and very stacked architectures where you had the specialized modules doing one thing for one specialized things, and then you compose them. But in the past years, this has evolved greatly towards two main families nowadays, which are the AA-based compound and the end-to-end holistic. The difference is that also the similarity is that both of these have large neural networks inside, so they're optimized together. But the one on the right-hand side, the end-to-end holistic, you just have one neural network that takes you from the pixels to the decisions, while this one has some intermediate specialized neural networks that deal with that. So in general, in practice, you will have to strike a trade-off between the needs and what's possible. I'm just outlining the trade-offs that you have here when going from left to right. So as you go from left to right, and also to more recent architectures, you have more data, more compute, bigger models, but in the same time, you also have fewer manual annotations because you rely a lot on raw data, and we'll come back to that. The architectures are simpler, and you have far better models. So we're in general evolving about these two in the current state-of-the-art architectures in driving. So especially these two are relying on a key component, which are foundation models. So foundation models is any model that is trained on raw data, in general using self-supervision and at a large scale, and then you can adapt this model to different downstream tasks that are useful for you. The interesting thing here, especially if you consider driving, is that you can exploit knowledge from around the web, the internet, from different data distribution to inject that in your model, and then you can use it for your specific application of driving. If you just rely on driving data, well, the car does not see so much. It's just driving. It's just roads. It's a very limited experience compared to what's happening in the world. So if we speak of foundation models, there's actually a landscape of different foundation models nowadays, and I would invite you to take a dive into that. So I categorize them into three main families of foundation models. So we have the closed weight citadels. So these are models that several players follow. So this means that the models are closed weights. You have no idea how they were trained, on how much data. They're usually behind an API, they're black box, or they're developed directly in the product. So there's no way for the others outside to understand them, to improve them, and to contribute them. Or they might have some backdoors. They might have some vulnerabilities that they might be not known to the original developers. Then you have these open weights model. So these is models that are where you have the checkpoints released to the community, but you have no idea on the data that it was trained on. So here you have recently you have seen the Chinese LLMs models that are very good in producing such models, but at the end of the day, you have no idea what's inside. Again, if there are some structural biases in this data and so forth, vulnerabilities, it's difficult to figure out. Finally, we have the Open Science Pavilion. So here, everything is in the open, meaning the data, the code, the intermediate checkpoints, and the final ones. So this is very useful to debug the model, to explain it, and also to find new ideas on how to improve it, and also to involve other people in the community to contribute to that and improve it. So this approach is followed by very few players, in particular academia, but also an axis that we follow as well in our group. So moving forward to show you how we are trying to be this open pavilion with some of our models, I will describe you two approaches that we have proposed at Valeo that are following this philosophy. So the first one is Franca, which is comes from French and from free, which is the first fully open source foundation model that actually matches proprietary Tier ones. So what we do here in Franca, so we train the model without supervision. So this means look at the raw data, and we obtain a suite of pre-trained vision transformers that are trained on a large uncurated set of publicly available data. So it's a data set of 600 million images, and this is a different from the other approaches that are proprietary and that curate the data, but at the end of the day, you have no idea what's inside. There were some other works that tried to do on uncurated data. So just to explain that we do not do it just for the purpose of having open models. We also want them to be good. So there were other models that tried even to train on even larger data sets of 2 billion images, but they were not that great. So here's where we come with our model. We release everything, checkpoints, code, data, such that other smaller or bigger teams can build on it, tinker it, break it, and of course improve it. So a thing that I would like to highlight is that we also bring some innovations at the level of the pre-training, but also at the level of the post-training. So the code is there, and also the paper, you can have a look. I will not go into details, but it's just not a reproduction of what's existing there in closed models. So looking a bit at the performance, just to defend this point, we look at different downstream tasks, that are interesting for driving. So they're dense perception, out-of-distribution detection, and 3D understanding. And we can see that our models that are in green, so the size of the circle is how big is the model. So the small circle is a 300 million parameter, the bigger one is a 1 billion million parameter. So we can see that our model is better already than the pink one, which is the previous open models, and also better than some proprietary ones like DynoV2 across these tasks, right? So this is actually, we wanted to have a useful model, and we'll see later on why we wanted to have it useful. So when we look inside the features, what it understands. So I'm just depicting here the features, the pixel level predictions that this model is making. So I remind you there were no labels involved in training it. So we can see that similar pixels depict the same class, right? So this is the image, and we see that the pixels from the plane are very similar, the ones from the truck, from the air track, and so forth, also from the cyclist. So we see that these properties of detecting objects emerge in the features of these objects, in these models, and this gave us the idea of using it for driving, right? So how do we use these features for driving? And then here I'm entering in our second topic of today, which is our video-generated models by Wim and Baba. So again, this is also a teamwork that we released a few months ago, and I'll walk you through the intuition. So currently, I'm taking a look here at the driving agent. For some reason, I don't have the video. Let's see a look. Okay, I'm sorry. So what I wanted to show you here, for some reason it does not work, is that we can generate, so it was here. So what should be visible here, we try to play it here. Okay, this is what's unexpected. It's a link, but I have the internet. I have the internet connected. I seem to have the internet connected. Let me just reload it. Now, maybe it will take it now. Just get some prayers. For some reason, you cannot play the videos, which is not worse. Yeah, so what I would have shown you here is an image with a driving agent. We simulate an adversarial event where a car comes in front of us and any agent, most of the agents are just crashing into it because it's a situation that he has not seen. You have a car coming your way. Okay, so what our solution is to that? So why is these types of events happening? Is that in general most of the agents that we have for driving nowadays in state of the art do not have the capability to explicitly predict what's happening in the future. So this is why we propose to look at to train a driving world model that is to predict the future of what's happening in my videos. So for example, here you can imagine that I have this video of a car. So my model will predict what is happening in the future frames of this video. Okay. So what I was planning to show you here is that we can get to have these models that starting from some real video frames will end up in producing synthesizing videos of what's happening next in the video. So here I would have had this car that comes in this way, and my ego vehicle goes that way further, and you will see different vehicles incoming to that, and the model is able to predict that quite well. So if we integrate this type of reasoning in our model, and then we put it in a driving agent in the same scene, you would have seen in this video how my car is avoiding this adversarial object. So what is VABIM and VABAM? So so VABIM is a video generation model that is coupled with an action expert that is supposed to help us with the planning. So for the first part, VABIM, what we do, we train, just like GPT, a model to predict the next tokens. But here the tokens are just image patches, and we train it on the largest publicly available data set at that time. So it was 1,800 hours. Compare that to the biggest academic data set that was available at that time, which was about 100 hours. So we went on scaling up further this type of models. So how it works into detail. We take a video sequence, we decompose the images into patches, and we convert these into tokens. And just like GPT, where an LLM is predicting the next word, we predict the next patches. So to simplify our life, we need to convert these pixels into tokens. So here we are using our Franka model to produce these patch tokens that are then fed to a GPT-like autoregressive predictor that will predict the last patch at all time, right? So I'm seeing here the first 10 patches, and then the 11th patch is this red one that my model needs to predict. So this is very scalable. Okay, now it seems to be working. So this we are seeing what we're generating with our model. So starting from a few real frames, then it can predict the future and what will happen in the scene. But this is just video generation. We want to do driving. So for driving, we equip our VABIM model with this module that does the driving part. Essentially takes the feature from our video generation model that knows to predict the future and maps these to actions. So we just use a few hours of data with commands, with controls to adapt our model. So this is how our VABIM now is able to predict, to do decisions in adversarial settings. So here we have put our model in a simulator where we put again a very difficult scenario where you have unexpectedly a truck coming our way, and the car is taking a decision that is a bit outside of the rules to avoid the accidents and avoid this truck by the right hand side, right? So this is how we avoid this accident, and this is due to the fact that our model was pre-trained on vast amounts of data on the internet where it had seen these types of behavior. Imagine these Russian dash cams. There might be things in the data. So what's interesting for that is that after we have released the model, some other labs took it over. So this is work from NVIDIA, and they used our VABAM model for winning the HackSim challenge. So there was a new simulator, a new evaluation benchmark that appeared that was much more difficult than the one where we tested before. they took our model, they fine-tuned it a bit, and they managed to win the challenge over other NVIDIA teams and some other labs that we entered this competition. So to wrap up, what I want, my messages are here today is that competitive open source foundation models can enable progress, faster progress, sorry, and it can involve multiple stakeholders to solve these problems. We can see that we obtain big leaps in solving autonomous driving, and we can do that without hyperscale data. This does not mean that we do not need large-scale data. So this is why we're working on putting these models out there. But we do not need thousands of more times the more data than many players do. Also, focused research by small teams can go very far, and we're looking forward for the next stage of that. So to have more data that will be available to the public, we're starting a partnership with Natix. So they're a startup that are crowdsourcing data from Tesla vehicles, and together we'll be working to have open world models for driving. In this case, with multiple cameras and with more data released to the public. And that I would like to thank you for your attention.
In terms of the next session about scaling AI sustainably with Fujitsu Monaco. If you have one question, maybe, or you can ask everyone.
Sorry for the
Question after that, of course.
Yes.
Hello. How can you be sure that the video generated by the model is the video or the image generated could be actual or possible things that could happen in a scenario?
So you mean how do I make sure that I have in my data these adversarial scenarios, or how do I make sure that it does well on these adversarial scenarios?
How can you be sure that the scenario that generated by the AI can be a possible scenario in real life?
Okay, so we don't. We don't. For us, this generation of the pixel is more like a supervision signal that is cheap to acquire, but we do not need to generate pixels, right? So we remove that head, and then we fine tune it with some supervision to generalize, to make it drive better. And then it's a matter of also how do you fine tune it and how do you add other guardrails to these models, right? So here is still early prototypes. It's not something that I would put in the car, right? It's still not ready. We're exploring how far can you go with these types of models that we know are big, can reason, what are the limitations, where does it work, and so forth, such that for the next products, the future products that Valo and other companies will be making, you are sure that you know the weak points and the strong points of these models, and you integrate them in the product, and the product needs to be safe all the time, right? So it's more exploratory at this time. Thank you.